Okay, welcome to the Homotopy Type Theory Electronic Seminar Talks, the hottest seminar on the planet. This week's speaker is Niels van der Weide from Radboud University, and the title of this talk is Constructing One-Truncated Finitary Higher Inductive Types as Groupoid Quotients. Go ahead.
Thank you for the introduction, thank you for the invitation, and thank you all for attending this seminar. In this talk, I'll show how to construct one-truncated higher inductive types using the groupoid quotient. So let us start by recalling what higher inductive types are, and to do so, we use a couple of examples. So the main feature of higher inductive type is that it is a mechanism to define types by describing constructors for the points, paths, two paths, and so on. So usually in type theory, you have inductive types, where you only say how to construct points, like for the natural numbers or list. But in higher inductive types, you also can give constructors for paths. So an example would be the circle, this one, S1. It has two constructors. The first one is a point constructor, base, and is of the type S1. The second one is a path constructor, loop, and is a path between base S1 and base S1. So this type cannot usually be expressed as an inductive type, and if you assume the univariance axiom, you can also prove that a loop is not equal to reflexivity. Another example is the torus, T2. And again, this type has a point constructor base. But now there are two path constructors, loop L and loop R. Both are of type base equals base. But this type also has another feature of high inductive types, namely that you can have constructors for paths between paths. And in this type you have serve, which is a path between loop L concatenated loop R. So this symbol denotes path concatenation, and loop R concatenated with loop L. So in higher inductive types, you can have both constructs for points, paths, and higher paths. But there are other features you might desire from higher inductive types, such as recursion. An example would be the integers modulo 2. This type has two point constructors, Z, which is just a point, but you also have a recursive constructor S, and this constructor takes an integer modulo 2 and returns another integer modulo 2. And there also are two recursive path constructors, M, which depends on this X of type Z2, and a two-path constructor, C, which also is recursive. In this type, you see recursion only with points, so only with elements of Z2. But in higher inductive types, you might also have recursive path arguments. So are paths between points of the higher inductive type being defined. An example would be the set-truncation, this one. You see that in trunc, there are two path arguments, P and Q, which are of type X equals Y. So in general, you also would like to have that the path constructors or higher path constructors can depend on arbitrary paths. So let us now look at some words mentioned in the title and say what they mean. The first one is finitary, and finitary means that every recursive constructor only has a finite number of recursive arguments. The way we will later do this formally in the talk is by using finitary polynomials. An example of a finitary in higher inductive type would be H1 here. So here you have a constructor C1, which has two recursive arguments. A non-example would be H2, because in C2 you have an infinite amount of arguments of H2. So you have an infinite amount of recursive arguments. Another piece of terminology in the title is one truncated. And we say that the type is one truncated if for every 2 points x and y, every 2 paths p and q of type x equals y, and every 2 r and s of type p equals q, we have r equals s. You can think more systematically about this definition by using the terminology of n truncated. So -1 truncated would be that every 2 points are equal. 0 truncated would be that for every 3x and y, the type x equals y is -1 truncated. And 1 truncated would be for every x, y, the type x equals y is 0 truncated. The last piece of terminology from the title I will briefly mention here is the groupoid quotient. The groupoid quotient is a higher inductive type that takes a groupoid and turns it in a one type. It is basically a generalization of the normal quotient, but with equivalence relations replaced by groupoids. Later in this talk, we will discuss this one more formally. So the main problem we will address in this talk is how to reduce finitary one-truncated higher inductive types to simpler principles. So in this case, we would reduce it to a single higher inductive type, namely the groupoid quotient. To do so, we take the following steps. We start by defining within type theory the notion of a signature for a higher inductive type. And the one we will discuss in this talk allows for points constructors, path constructors, and two-path constructors. Not higher because we're interested in the one truncated case. So higher path constructors would be trivial. For each of these signatures, we define introduction, elimination, and computation rule. And from that, we get the definition of a higher inductive type. So the elimination rule will be restricted to eliminating into one types because we're only interested in eliminating into one types. After that, we show that each signature has a higher inductive type in one types if we have the groupoid quotient. So we basically, what we do is we construct higher inductive types from the groupoid quotient. Note that the higher inductive types we're interested in all are finitary. That explains the finitary part of the title. All of the results are formalized over Unimod. And for those who like reading COG code, here is the link. So what will we treat in this talk? Well, we will start by discussing the theorem in a simple case, namely for set-truncated higher inductive types. Basically, the approach will be similar, but the terminology and the used machinery will be more familiar because it will only use category theory. After that, we will discuss how to generalize this argument to the one truncated case. So what we do for that, if we translate notions related to sets to notions related to one types. We follow up by discussing the one truncated case, and we discuss the following things in more detail. We discuss signatures, bicategories of algebras, and since we'll use the groupoid quotient, we will not only discuss algebras in one types, but also in groupoids, because what we'll do is we show that if we have an algebra in groupoid, we can take the quotient of it, the groupoid quotient of it, to obtain an algebra in one types. So after discussing the groupoid quotient, we can then show that the groupoid quotient gives rise to a bijunction between these two bicategories of algebras. We finish by concluding and giving an outlook and further open problems. Okay, how are we going to construct set-truncated higher inductive types? And the main idea will be to use the quotient. So we will take the following steps. So first, we start by defining signatures, because then we can say precisely what higher inductive types are supposed to be. After that, we define categories of algebras, and we prove initial algebra semantics. introduction rules for the points, paths, and so on are given by the algebra structure, while the elimination and computation rule are defined when proving initial algebra semantics. After that, we show that we have a junction between the category of algebras in sets and in setoids. And then to construct the higher inductive type is suffices to construct the initial algebra in setoids, which is more doable than constructing the higher inductive type directly. We'll discuss the red items in more detail. The other part, so initial algebra semantics and how to construct the initial algebra in setoids, we will not discuss further, but it is needed to make the argument complete. So let us discuss what set-truncated higher inductive types are. And basically what we are going to do is we're going to look at higher inductive types of the following shape. We have a point constructor, we have a path constructor, and the higher inductive type is forced to be set-truncated. As a consequence, we can only eliminate this higher inductive type into sets. So if we would like to define signatures for such higher inductive types, we must specify what P, J, Qj, Lj, and Rj are. And P and Qj are given by finitary polynomials. So what are finitary polynomials? Well, a polynomial describes or represents a functor on sets. And it's not just any functor, it has to be one of the following four constructors. Either it is a constant functor, so constantly a set A, or it is the identity functor I. It could be a pointwise sum or a pointwise product. So the type of polynomials is inductively generated by these four constructors. And the main point is that a polynomial represents a functor on sets. And for some notation, so if we have a polynomial and a set, then we can obtain another set by applying that functor to a set. And we write that as follows, so just Px. So if we return to the shape of the higher inductive type we were discussing, we can already say what a part is going to be. So P is going to be a polynomial, J is going to be a type, because J just represents all possible path constructors, all path constructors in this higher inductive type, and Qj is going to be a polynomial. It is the arguments of our path constructors depend polynomial on the higher inductive type being defined. So now we need to specify what Lj and Rj are. And for that, you need to note first that there are some dependencies. So when we were defining the circle, the path loop depends on the constructor base. So the path constructor depends on the point constructor. So P depends on C. So when we're defining all possibilities for Lj and Rj, there must be a parameter P which describes this, the type of the point constructor. Furthermore, we also need a parameter representing Qj. So the type of the polynomial describing the arguments, the point arguments for this constructor. And you see that in the type of path endpoints. So Lj and Rj are, I call them path endpoints in this presentation. So here there are three polynomials on which are the parameters. So first of all, we have A, that is just of the point constructor. S is the argument. But you might be surprised that there's also a T. And the reason for that is that such a path endpoint will represent a function like this. So if we have a path endpoint of type EAST, then we can, on a type with a function AX to X, we can represent it as it represents a function like this, which can make use of C. And to make such functions composable, the source and targets must match. So for that reason, we also let the target depend polynomially on the higher inductive type being defined. I won't show you all constructors for the path endpoints, but just a couple. So here you have 3 constructors for path endpoints. So first of all, you have the identity, which represents the identity function, and you have composition, which is the composition of functions. There also is a constructor, which represents the point constructor. So in the case of the circle, this would represent base. And there are many others, like the first projection, in left, and so on. But from these 3, you can already see why the t is necessary, because in general, this p won't be equal to I. So if you want to have all constructors like this, you need to allow for arbitrary targets. And for that reason, you also have that t. So Lj, Rj will be path endpoints. And now we can fully say what a higher inductive type signature is for set-truncated higher inductive types. So if you look at the shape here, you see that it consists of the following data. First of all, you have a polynomial A. This represents the point argument. Second, there's a type JP, which represents all labels for path constructors. And for each j in JP, there must be a polynomial which represents the arguments of this path constructor. And to endpoints, Lj, Rj, which represent the left and right hand sides of the path constructor. So this is we will construct these higher inductive types in this part of the talk. So let us recall the structure of the argument. So now we have defined signatures. And the next step is to define categories of algebras in Boyd sets and setoids. For those who did universal algebra, the approach done here will be not surprising because it is just standard. So what do we do? Well, let us first think about what an algebra is supposed to be. And what an algebra is supposed to be can be read off from the shape of the higher inductive type. So since we have a point constructor going from age to age, we must have an operation like this. Furthermore, their equations are supposed to hold, and these also can be read off from this one. So you need to have paths like this. And lastly, since we're working with set-truncated higher inductive types, the carrier must be a set. If you look at this, then in this part, you might recognize algebras for a functor. So A will represent a functor. So this will be like algebra for a functor. And since X is set-truncated, this equality type will form a proposition. So all the equalities just form a proposition, and thus we can use the full subcategory. So let us quickly recall these 2 categorical constructions. So if we have a category C, an endofunctor on that category, then we have a category F-al F, and the objects of that category are pairs X with a map Fx to X. So this does the point constructor. Secondly, we have the full subcategory. So suppose we have a category C and a predicate on the objects of C. Then we have a category F sub CP, and the objects of this category are just objects X of C with proofs PX. All the morphisms of C are homomorphisms in F sub. So we'll use the first one to do the point constructor, and the second one to do the path constructor. Let us be briefly more precise. So if you have a polynomial, we can interpret it as a functor like this on sets. So if we have a signature sigma, then we can define a category pre-al sigma, and the objects of that one are called pre-algebras of sigma. It is just a category of algebras on the interpretation of A sigma. I call these pre-algebras because they do not satisfy all introduction rules yet. They don't have all structures yet. So let us write U for the forgetful functor from the pre-algebras to sets, and we'll use this one to interpret endpoints. So the high inductive type is not only given by a point constructor, but we also have path constructors. And these path constructors have a left and a right endpoint. So we also need to interpret endpoints. And for that, we'll use natural transformations. So suppose we have an endpoint like this. So here we have the point constructor of sigma, and we have source target. Then we have a diagram like this. So here we have a functor from pre-algebras to sets. We have two functors from sets to sets, namely S and T. And then each endpoint can be interpreted as a natural transformation like this. Note that because we start with the pre-algebras, we also have access to the algebra map when defining the natural transformation. And this is how we can interpret endpoints. And now we can define algebras. So we define the category of algebras as a full subcategory of pre-algebras. And in the category of algebras, each object xc needs to satisfy the following rule. And that just says that if for each label of the path constructors and each argument, we have this equality. So that is the equality described by the path constructor. I said that we need to define algebras in both sets and setoids. And for setoids, we have the same approach. We first define pre-algebras as the category of algebras on an endofunctor, which is just done by interpreting polynomials on setoids. And then we define algebras as a full subcategory of the pre-algebras. So this is the second step. So we have the category of algebras now. And as said before, initial algebra semantics is needed for the arguments, but we do not discuss it in more detail in this talk. So we'll just cross that off the list as well. So the last step of the set-truncated case, which we'll cover in this talk, is how to lift the quotient to an adjunction between the categories of algebras in sets and in setoids. So let us briefly recall the quotient. So we start with the set X and the equivalence relation R on X. And recall that the setoid is precisely the same data. So I could also have said we start with the setoid XR. The quotient X modulo R is defined as the following higher inductive type. We have a constructor class which says that each point in X gives a point in the quotient, and these points are identified according to the equivalence relation R. Furthermore, the quotient must be a set. So this gives a set, and yeah. The important property of the quotient is that it gives an adjunction between the categories of setoids and of sets. So let us write sets for the category of sets with functions and setoid for the category of setoids with functions that preserve the equivalence relations. Then we have two functors, quot, which goes from setoid to set, and path setoid. It goes from set to setoid, and it sends a set X to the setoid X with the path space. So the equivalence relation is just equality. And then the important result here is that that quot is a left adjoint functor, and that path setoid is its right adjoint. This was originally proven by Egbert Rijke and Bas Pitters. So now we will lift this quotient to the categories of algebras. And since we defined the category of algebras in 2 steps, we will also lift the quotient in 2 steps. So first we need to lift the quotient to pre-algebras, and after that we lift it to algebras. So since pre-algebras are defined as as the category of functor of algebras on the functor, we already can use results known for this category. And a particular one is by Hermida and Jacobs, and they give conditions to show to lift a junction between two categories to an adjunction between categories of algebras. By applying this result, we can lift the quotient to a junction between pre-algebras in sets and pre-algebras in setoids. And what's important to notice is that on the first coordinate, this is the quotient. And on the second coordinate, you do the interesting part. The main idea for defining this functor is that polynomials commute with quotients. So the quotient commutes with polynomials, and that way we can also obtain the right algebra structure on sets. This is also the point where we need that P is finitary. We can't allow an infinite amount of recursive arguments here, because otherwise we would need the axiom of choice to show that the polynomials commute with quotients. And this was originally observed by Chapman, Ustalu, and Veltri. And to obtain a junction on the level of algebras, we use that algebras are defined as a full subcategory, and for that it is not too difficult to lift the adjunction. What you do is that if you have a pre-algebra in setoids, if it is an algebra, then so is the quotient. And you also need to show that for the pod setoid, and that way you can obtain the desired adjunction. So now we can conclude the set-truncated case. So if we want to construct a high inductive type on sigma, by initial algebra, it suffices to find by initial algebra semantics, it suffices to find the initial algebra in sets. By junction, it suffices to find the initial algebra in setoids. And this one can be constructed. So you can find it in both the formalization and the internship report by Moenclaey, which he did with Dybjer. It is a bit technical construction because you need to guarantee that all the right constructors are there, and that makes the definition a bit long. Concluding, each signature has a high inductive type in sets. So this talk was actually more about one type. So the question is now, how can we do this for one types? So how can we prove the following? Assuming that we have the groupoid quotient, how can we construct a high inductive type in one types? Basically, we will use a similar approach, but we need to make some modifications because there are some differences between sets and one types. So sets themselves form a category, and recall that in homotopy type theory, the morphisms in a category are required to form a set, and this is set aside by sets, so it forms a category. However, for one types, the morphisms do not form a category, and for that reason, we need to go higher. We should use higher categories. Instead of a category, they form a bicategory. Furthermore, a one type has points, it has pods, but all structure above of the pod space is trivial. That means that if we would define one as a quotient, we would need to take all of this into account. So for the quotient, we would use an equivalence relation, which gives points and equalities. But for one type, we want to have points, equalities, and equality between equalities. And this structure is given by a groupoid. So with all this, we get that the analogous notions of one types to those in for sets. So setoids, the analogous notion for one types is groupoid. For quotient, it is groupoid quotient. For category, it is bicategory. And then we make use of all kind of notions from category, like initial object, functor, natural transformation, adjunction. And for all these, we also have an analog, namely by initial object, pseudofunctor, pseudo-transformation, bi-adjunction. So let's also fix some notation for the bicategory of one types and groupoids. So the bicategory of one types, whose one cells are functions and two cells are paths between functions, is noted by one type. And the bicategory of groupoids with functors and natural transformation is denoted by GRPD. To obtain the approach for one truncated high inductive types, what we do is we take the approach for set-truncated high inductive types and we replace the notions for sets by notions in one types. So we replace set-truncated by one truncated, category by bicategory, set by one type, setoid by groupoid, initial by bi-initial, quotient by groupoid quotient, and adjunction by bi-adjunction. And this is the approach to construct high inductive one types, and it's basically essentially the same as for sets. However, because we're working with higher categories, it is more complicated and more technically challenging. Again, we will discuss in more detail the following steps. We'll show how to define signatures. We'll show how to define bicategories of algebras in both one types and groupoids. And we will discuss how to lift the groupoid quotient to a bi-adjunction between the bicategory of algebras and in one types and in groupoids. The high inductive types we consider in this case are of the following shape. And this is similar to the work by Dybjer and Moenclaey in their MFPS paper. The high inductive types are of the following shape. We have a point constructor, a path constructor, and a constructor for two paths. And parts of this definition is similar to the high inductive types in the set-truncated case, namely for the point constructor and the path constructor. So A will again be a polynomial, JP will again be just a type, SP will be a polynomial, and LJ and RJ will be path endpoints. But there's also something we didn't have before, a two-path constructor. And there are two interesting parts of this definition. Namely, how do we represent the path argument, and how do we represent the left and right-hand side of this equation? For RJ, which is just the point argument, we can again use a polynomial. So we will discuss we will discuss these four ingredients, these four in more detail. We start by AJ and BJ. If you think a bit about it, let's return to the example of the set truncation, because that was the example where we had the path arguments, and that one looked as follows. The path argument was PQ of type X equals Y. So what you might expect is that you would have like a list of pairs of endpoints. The pair represents the left and the right hand side, and the list just says that you have a finite amount of these path arguments. However, with a trick, you can restrict yourself to a simpler case, namely in a case where there's only one path argument. That is because you can rewrite this high inductive type as follows. Instead of assuming that you have PQ of type X equals Y, you only assume you have P of type X, X equals Y, Y. To obtain the desired left and right hand side, you need to modify them a bit by taking the first and second projection of the path. For this reason, we shall represent the path argument by two path endpoints, where we allow the target of these path endpoints to be an arbitrary polynomial. So these were aj and bj. So now we need to look at bj and qj. Here we define a different notion of endpoint, which I will call homotopy endpoint. Let us first think what these will depend on, because there are a lot of dependencies. These should be able to mention the point constructor and the path constructor, which we already gave before. So that means that the definition of homotopy endpoint will depend on a polynomial a type jp, and for each j you must have a polynomial and two path endpoints. But we also have more. The homotopy endpoint also depends on the path argument, the point argument, and the path argument. So we also must give this data. So the path argument, the point argument is represented by a polynomial, and the path argument is represented by polynomial t, and two path endpoints, which is the trick we discussed before. Given all, okay, this is all the data, but each of these paths, so the paths we have here, they must have a source and a target. They are not just any paths. So you say that you define the type of homotopy endpoints with source S and target T. So you also must give two path endpoints which describe the endpoints of the path we are describing. Given all this data, we define the type of homotopy endpoints by induction. This type has quite a lot of constructors, and I won't show any of them. The constructors you can think, which you can think of are like the identity path, inverses, composition, applying the point constructor, like up the point constructor on some already given path, or more, one of the path constructors you gave, or the path argument. So there are quite a lot of them. But the main thing you need to take away here is what it represents. So if we have a type X with the desired point constructor and the desired path constructors, then a homotopy endpoint represents for each X of type Rx and each W of this type, it represents a path like this. So this is the point argument, this is the path argument, and here you see that you have S and T, which describe the left and right hand side of the paths being defined. Let us quickly go back to the definition and recapitulate it a bit. So A, JP, SJ, LJ, RJ are, as we discussed before. AJ, BJ are path endpoints. BJ and QJ are homotopy endpoints. I won't give the precise definition of the high-inductive types we consider, because the dependencies make the definition quite complicated to read. So I hope that if you take the scheme here into account and how we represent each piece of data, I think that gives a clear idea on what the scheme is supposed to be. Okay, so now we have defined signatures. So the next step is to define a biojunction between the, sorry, I misspoke. The next step is to define bicategories of algebras. And for that, we need to think a bit ahead about the biojunction. So when we are defining a biojunction between categories of algebras, so we go from algebras on sets to algebras on setoids, then the functor takes an algebra and returns an algebra. And for that algebra, we need to give both components. However, what we're doing, we're lifting functors. So the first component is actually just the functor we already have. But if we are defining the functor on algebras, we actually need to redefine it. We need to do it again to show the functor laws. And that makes formalizing it quite tedious. You need to redo a lot of work, and that is not really how you want to do a formalization, because then you will get too much, then it will just be more complicated than it needs to be. Instead, we'll use a trick to define the bijunction component-wise. So instead of defining a bijunction in just on the level of algebras, so by defining functors between algebras, and then you have the bijunction, we define it component-wise. So we need machinery to define bijunctions and bicategories this way. And for that, the machinery for that is displayed by categories. They allow you to construct bicategories of which objects are like sigma types. Let us discuss displayed bicategories a bit more precisely. So a displayed bicategory represents properties and structure to be added to objects, morphisms, and two-cells in some bicategory. The definition is as follows, but in this definition, we will think of B as one-types. D represents algebra structures. So D is not algebras, it is algebra structures. So what does a displayed bicategory consist of? Well, first, we have for each object in B, we have a type of objects over it. For one type, an algebra structure, this would be for each one type, we have a type of algebra structures on it. Secondly, we have for each morphism and objects over X, the domain and codomain of this morphism, a type of one cells over this morphism. In our example, what we have, here we have a function between one types, we have an algebra structure on X, we have an algebra structure on Y, and then this represents the type of proofs that F is a homomorphism. So that F preserves the algebra structure from X to Y. And we need to do the same for the two cells. So then we have a two cell in B and one cells over F and G. And then we need a set of two cells over it. These just represent two cells, which two cells, the structure to be added to the two cells. The whole definition is a bit long and complicated because you need to say stuff about the associators, unitors, identity, composition. But this represents the main idea, what kind of structure you will add to the objects and to the morphisms and the two cells. If you're interested in a full definition, you can find, take a look at the paper by Benedict Arends and other people. And if you're interested in this for the categorical case, so display categories, you can look at the paper by Arends and Lamstein. One of the important points of displayed bicategories is that they give rise to total bicategories. So in this picture, it would be as follows. So B is the bicategory of one types. D represents algebra structures over one types. And total D would then be the bicategory of algebras. What is an algebra? It is just a one type together with an algebra structure. So you take the pairing. And you will do the same for the morphisms and two cells. So the objects are just paired with something in the B and something over it. The morphisms are pairs of a morphism in B and a morphism over it. And the same for two cells, just a two cell in B with a two cell over it. Another important thing is that you always have a projection pseudofunctor, which goes from the total bicategory to the base. It just takes a first component of each object, each one cell, and each two cell. This takes if you would look at like algebras, then here you have algebras in one types, and here you have one types, and this just takes a carrier, so the underlying one type. We will define several display bicategories, which will help us to define bicategory of algebras of high inductive types we consider in this talk. So what kind of structure does an algebra for our high inductive types have? Well, first, you have the point constructor. So you need a displayed bicategory, which adds the structure for the point constructor. Second of all, you need to have the path constructor. And for that, we will also define a displayed bicategory. And lastly, we need to have the third one, which is the homotopy constructor, or the two-path constructor. And for each of these three, we will define a displayed bicategory, which adds the desired structure to the bicategory. For the first one, we'll just use algebras on a pseudofunctor. For the last one, we will use the full subbicategory, because equations like this form a proposition, since we're looking at algebras in one-types. And only for this one, so for the displayed bicategory that adds the structure for the path constructor, we will introduce a new one. So let us start by algebras on a pseudofunctor. And for that, you need to note that the observation why this is useful is that every polynomial p gives rise to a pseudofunctor on one-types. That is why we can apply this construction to our desired case. And what you need to remember here, or what's the more important thing here, is that the objects over some object in B are just one cells like this. So this is just the algebra map you want. You also need to define the displayed two cells and the displayed one cells. These are a bit more complicated, and mainly due to technical reasons. So the displayed one cells are just represent the commuting square for algebra maps, and these have to commute up to invertible two cell. And the displayed two cells are just coherencies of these. So now we're going to think about how to add the path constructor to the structure. And for that, it is good to recall how we interpreted endpoints. We have, as before, we have this situation. We have the bicategory of algebras, we have the forgetful pseudofunctor, and we have two pseudofunctors on one type. When in the set-truncated case, each endpoint gives rise to a natural transformation. But now we're working in the bicategorical case, so instead of a natural transformation, an endpoint gives rise to a pseudo-transformation, like this. Let's try to keep this in mind and see how the following construction works. We have a displayed bicategory over B. So in our example, this was our case, this is like algebras on a pseudofunctor, and this is one types. Suppose we have two pseudofunctors S and T. These are just this one, interpretation of S, and the interpretation of T. And lastly, we have two pseudo-transformations L and R. This is, if you look at this, S projection, T projection. That is the same as what we had before, S projection, T projection. So L and R represent the left and right-hand side of the equation. So now we're going to define a displayed bicategory over the total bicategory of D, and the objects over X. So X is in this case a pair, are just two cells like this. So this is, if we would look in one types, then the two cells are just equality. Then the left and right hand sides are functions, and then this would be pointwise equalities. The displayed one cells and displayed are a bit more complicated. This is just a coherency, and I only added this for completeness for those who want to read the slides afterwards. And the displayed two cells are just inhabitants of the unit type. The last displayed bicategory we need is a full subbicategory. And this one we will again define as a displayed bicategory instead of directly. And this one is more simpler than the previous ones. So suppose we have a bicategory B with a family of propositions on the objects of B. Then we define the full display bicategory as follows. Objects over X are just proofs of Bx. So in the total bicategory, you will have a pair of an object in B and a proof that B holds for it. And for the displayed 1 and 2 cells, they are just units. So the displayed 1 cells are just a pair of the displayed 1 cells together with dt, which is just the same as a one cell in the base. So the 1 cells in the total are the same as 1 cells in the base, and the same for 2 cells. So this is really the full subbicategory. So now let us see how we use this to get the bicategory of algebras. And this is again done in multiple steps. But since we have 3 pieces of data, we do this in 3 steps. So first we consider pre-algebras. These are a pre-algebra consists of a 1 type with the required function, so the point introduction rule. Then we look at odd algebras, and for this one we need pods like this. So, we define this displayed bicategory using df cells, so the second one we defined before, and this happens on top of pre-alg sigma. So we define the bicategory of algebras in several layers. So first we look at the point introduction rule, so pre-algebras. Then we look at the pod introduction rule, so pod algebras. And at every step, 1 component of data is added. So here we have 1 component, namely the function, and here we have the pods. And lastly, we define algebras by adding the last component, namely the introduction rule for the homotopy constructor. And this is done via the full subbicategory because we are working at 1 types. So then we get algebras the way you would expect them from the signatures. So they satisfy the introduction rule you would expect. For groupoids, we can do the same thing. Again, we need to define pre-algebras, pod algebras, and then algebras. And we can use the same constructions to define the same bicategories. We just need to play around with interpretation because we need to interpret all polynomials, path endpoints, and so on groupoids instead of on 1 types. But it's done the same way. Okay, so now we have defined the signatures, we have defined bicategory of algebras, and the last thing we will discuss in more detail in this case is the groupoid quotient and how it gives rise to a biojunction between the bicategories of algebras. The groupoid quotient is defined as the following higher inductive type. And if you look at it, you can compare it a bit to the quotient. Parts of it can be recognized. GCL is namely the same as like class of quotient. It just takes the class of an object in G. GCL is just identified, so it's like the class of. Not class of, it's like when 2 classes are equal. It says when 2 classes are equal, and this happens according to the morphisms in G. But there are 2 constructors which we did not have before, namely GE and G-concat. What these 2 constructors say is that the pod space of the groupoid quotient corresponds to the groupoid itself. That is because the identity pod is the same as GCL on the identity, and GCL also preserves composition and sends it to pod concatenation. So what this groupoid quotient really does, it takes a groupoid, it builds a 1 type whose points are just objects in G. The pods in G are the pods in that 1 type are just morphisms in G, and they have the same structure as groupoids. So the identity pod corresponds to the identity morphism, and the same for concatenation. Lastly, we have a constructor G-trunc, which says that it is a 1 type. The quotient is an adjunction, and the important property of the groupoid quotient is that it is a left bi-adjoint functor. And again, this is done in a similar fashion. So the quotient gives rise to a pseudofunctor from groupoid to one type. And this one will be the left bi-adjoint. So we also need to define a pseudofunctor in the other direction, which goes from one type to groupoid. I call this one the path groupoid, but you could also call it the fundamental groupoid. What it does, it takes a one type and it sends it to the groupoid whose objects are points in that one type. And the groupoid structure and the morphisms are just given by paths and the groupoid structure on paths in that one type. Then you can prove that G quad is a left bi-adjoint functor with a path groupoid as the right bi-adjoint. So now the question is, how can we lift this bi-adjunction? And again, we will use displayed machinery. So the reason why we used displayed machinery before was to prevent reconstruction. The ultimate bi-adjunction will be between algebras, and these have several components of structure. And what we want to do is we want to construct this bicategory component-wise. So on the first component, the carrier, it should just be the groupoid quotient. On the second component, so the point introduction rule, we want to define it using a displayed bi-adjunction so that we do it component-wise. And this is precisely what displayed bi-adjunction do. They say how to construct bi-adjunction by component-wise. Let me be a bit more precise about what they are. So suppose we have two bicategories with displayed bicategories on them. And we suppose we have a bi-adjunct between B1 and B2. Then what do displayed bi-adjunction help us with? Well, we use them to construct bi-adjunction between the totals, such that on the first component, it is given by the bi-adjunction we already had. And the displayed bi-adjunction specifies the second component. It does not say anything about the first component, that is just the one we already had. It just says something about the second component. So if we then construct a bi-adjunction on the level of algebras, we don't need to reconstruct anything. We just approach the problem component-wise. We do it on the carrier, then on the point introduction rule, then on the path introduction rule, and then on the homotopy introduction rule. And that way, we can define this bi-adjunction in a more modular and nicer fashion. So let us briefly conclude this argument. So how we will construct a high inductive type in one types the same way as for in the set-truncated case. Using bi-initial algebra semantics, it is sufficient to find the bi-initial algebra in this one. By bi-adjunction, it is sufficient to find a bi-initial algebra in this one. And this is something you can do directly. You can construct this bi-adjunction, the bi-initial algebra here directly. It's a bit technical. The definition requires a lot of constructors, but it is possible. So for details, you can see the formalization, and it can also be found in the paper by Dybjer and Moenclaey. So as a conclusion, all signatures have a higher inductive one type if we have the groupoid quotient. So what are some open problems and further work which is possible to do? So first of all, you can go for a more permissive syntax for higher inductive type. One extension would be higher inductive types introduced by Kaposi and Kovac. It would already be interesting to see whether in the set-truncated case it would all quotient inductive, all such types are constructible from the quotient. Another interesting problem would be to see how to generalize this construction to the non-truncated case. So where we don't restrict ourselves to one types. And another interesting open problem would be to see how to use the notion of high inductive type signature we discussed here to do algebras of bicategories and how it compares to established approaches to bicategories using to algebra in bicategories using two monads. Thank you all for listening. Are there any questions?
Okay, well, first of all, let's thank Niels for that talk. We'll do our usual silent applause. I'm the only one who gets to be heard. Okay, so yeah, are there questions? Well, I'd like to hear more about whether you have ideas about generalizing to the non-truncated case, or at least to higher truncation levels.
Okay, so if you would, okay, so the difficulty which would be the most immediate is you need to generalize bicategories to weak higher categories, and that is to do that inside of type theory. That seems quite difficult. However, I think there might be a possible solution would be by using wild categories. So what is a wild category? You take the definition of a category, but you don't require the morphisms to form a set. So you only have a part of the structure of a infinity category. This should still be sufficient to formulate notions such as adjunction and initial object. So that already gives a part of the argument. The other part then would be where infinities categories come up is with the groupoid quotient, because you would need to generalize the groupoid to a non-truncated, to a higher category. And even if you don't allow, even with just path and two-path constructors, you need higher morphisms in your category. You can't restrict yourself to something you can't restrict yourself to something with just one and two cells. So I think a possible solution there might be to do some kind of almost infinity category. I don't have a name for that, but what it would be is you have like as like an infinity category, you have objects, morphisms, two cells, and so on. And on these you only have the structure of composition, inverse, and identity. Furthermore, you have associativity and uniters, but you don't require any coherencies on these. That makes formulating this notion easier, and I think, but that is just a conjecture, that it might still work, but I don't know that for sure.
Okay, that's interesting. The hot Coq library has wild categories now. Mm-hmm. It's a recent addition, so it could be useful for that.
Yes.
Okay, other questions? Someone could ask about one of the other things on the future work slide. Well, okay, I guess, excuse me, I guess if people don't have more questions, we will just all thank the speaker again.
Thank you.
And I'll remind you that we meet again in 2 weeks, and our speaker in 2 weeks is Karol Szymiło. That's February 20th. As usual, you can see all our upcoming talks on the website, and there's also a link to the Google Calendar and a mailing list if you want to receive announcements. So see you all then.